Okay, welcome to our talk today for optimizing CUDA kernels in HPC simulation and visualization codes using Nsight Compute. John and I will go through our talk today for showing you how our NVIDIA developer tools help in optimizing kernel codes in VND and NAMD. To start quickly, I would like to quickly go over the Nsight developer tools. We offer three different tools: Nsight Systems, Nsight Graphics, and Nsight Compute. Nsight Systems is your system-wide data collector that creates the timeline where you see time-correlated data from the whole system, which includes CPU information like thread information, core information, as well as like API calls from various APIs that we support, CUDA, for example. And then we have Nsight Compute that is a kernel profiler that allows you to optimize the device code for a single kernel. And then we have Nsight Graphics as a counterpart to Nsight Compute that does the same thing for all the graphics APIs. This talk is actually like a part two of a talk that happened 2 years ago, where John and a few colleagues of mine optimized the same applications already with Nsight Systems and got good speedups by changing the host-sided code and the CPU code to make sure that the GPUs are fully loaded and get all their data most efficiently. And today we focus on the second part, where we show that the top kernels can still be improved and the things we found there, and show you how the tool helped with this. The quick agenda is I will introduce the new features that are introduced in the latest version that just came out, and then we go into VMD and NAMD and show, like with live demos, exactly what we did, so that you can see how we improved the kernel performance further. For those of you that didn't heard of Nsight Compute before, it's an interactive CUDA profiler for CUDA kernels. So the goal is you have a single kernel that you already identified as like something that you want to improve further, or it's like the slowest kernel in your application. And then you really deep dive into that one kernel and get a very detailed profile report by collecting hardware counters and getting as much information from the GPU back for that one kernel. And then you can iterate on that kernel, make it faster, and see exactly what you changed. The tool allows to kind of help your workflow by comparing before and after, so that when you make a code change, that you know exactly what changed. And everything we showed today that you have available in the UI is also possible to do on the command line. So if you only have a remote access to a machine, you can run the whole thing on the command line as well. It supports various systems, Linux, Windows as host and target, and then various ARM systems, PowerPC and Mac as the host as well, so that you can use it on a wide variety of kernels. I want to also mention it's highly customizable, so while we showed today all the standard sets that we ship with, you can modify the tool so that it fits like your needs the best. For the new version 2021, I want to quickly go over what's new, what we changed in the tool. So if you have used it already, that you know what's happening. We start out with the chips update. We add the support for the A100 GPU architecture. And specifically, we cover all the features that are exposed in CUDA 11 for that architecture. That starts with the device-sided CUDA async copy. You see in the cutout here quickly what that does is you can load data from the L2 cache directly into shared memory, and you don't have to go through the register file and kind of make two separate instructions that load the global data and then push the data back into shared. You can take this shortcut that directly places the memory into shared memory, the data into shared memory without having the round trip. Another improvement can come by sparse data compression. Here's an example from a report where we push like a lot of memory into L2. We send this down to like a compression unit that kind of cuts it down to a lot less, and then you can stream that out into device memory, and you can reduce, if you have sparse data, a lot of DRAM bandwidth by doing so. All the other features are also supported. Residency control, task graphs are fully supported, including all the hardware acceleration that was added for this. But to make all this happen, I also want to point out that we removed the GP10X Pascal support from the tool. They are still continued completely through NVProf and NVVP, so we still ship that, and support is not removed there. But for Nsight Compute, we removed it so that we can focus on the newer chips quicker and get all the tools out there. And not related to chips, but also something worth to mention, since Windows 7 support was discontinued, we also discontinued it in the tool. Coming to the changes for the actual report, when you collect it, we added a roofline analysis. For those of you that haven't heard of rooflines before, is like it's a very efficient, quick way to understand how close your performance is to given ceilings, and the ceilings are in our case given by the peak memory performance of the chip and the peak throughput for FP32 and FP16. And you can see in the screenshot, you see like where the little dot is where your kernel is, and the ceilings are what the GPU can do. And the closer that dot goes to the ceiling, you can understand not just like that you are now limited by the peak performance and that you reach the peak performance, but you can also quickly understand where there's headroom. You know, it's like you cannot maybe move further up, but you might be able to move a little further to the right. So it's a very efficient way to understand how that is, and it also allows to compare quickly between different architectures easier as well. We also revamped the memory cache tables. A lot of derived metrics like sectors per request, for example, is now in the table, and you don't have to calculate it in your head anymore. And we improved there a lot too, to make sure that we have make it most easy to kind of understand what the results are in the report. There are also a lot of workflow improvements that are not just like how the data is represented, but like how you interact with the report. We have hotspot tables, which allow to connect the data from the details page with the source page. In the screenshot, you see like we have the sampling data, and you can have links in here where you click quickly like where is the line in your large source code base with the highest sampling count. That was something that was available in NVVP, and we have that now as well in our tools, so we are closer in feature parity for that. We also allow, if you collect a report with a lot of results in it, then a lot of people want to filter the report down to something smaller, and that is currently possible with NVTX. So you have a filter UI where you can, after recording the results, can switch quickly and get to a shortened report that only shows certain results in an NVTX range that you can specify. We also allow on the source page that you can get aggregate metrics, which means like if you have a report that has only a single function or multiple functions, you can now collapse it and see the results at the bottom. That's the bottom screenshot where you can see for a single function kind of all the aggregate metrics. If you have large code bases, that helps a lot to kind of drill down into that. And we do have improved our rule system where you can access instance metrics and have links to other sections, which we will show in the live demo later too. Finally, some other bookkeeping. The names for the executables were quite long, including the extension for the file. They still work in the way they are, so we still have links set up for the old names if you have scripts that continues to work. But if you type it often, we have now shorter names that should hopefully make that a lot easier if you use the tool often, then less typing and less tab completion for all of these, so that should hopefully help a bit. And then we tried, I already mentioned it earlier, we tried to kind of improve on feature parity what was missing from NVProf and Visual Profiler. We do have the uncoalesced memory access rules now, and we do have the output placeholders for the process ID, environment variables, increasing numbers, and the host name, which is targeted for people that run this with an MPI start or something, and then that helps a lot to keep the output names consistent. And finally, we got a lot of feedback that there should be more documentation and more understanding of what those values all mean in the tool. there's a brand new kernel profiling guide that tries to kind of bridge that gap of the numbers that we show in the tool and the understanding of what the hardware does. So I encourage everyone who wants to learn more to kind of to look at the kernel profiling guide. There's also a new FAQ section in the documentation where a lot of the common problems that we see get addressed or like get answered, so that you can help, but you can continue asking in the forum and sending us emails too. That hopefully just shortcuts the time on your side as well. That was the quick introduction for the tool, and I want to hand it over to John now to give you an introduction to the use cases that we want to discuss today.
Hi, my name is John Stone, and I'm the main developer of VMD. VMD is a molecular visualization and analysis tool that we develop at University of Illinois, and its job is to take structure information that comes from cryo-electron microscopy, X-ray crystallography, and other sources. Use that structure information to prepare atomic detail simulations to be run on a supercomputer using other programs like NAMD, AMBER, and GROMACS. And among the different things that we do, the goal of these simulations is really to provide a scientist with sort of a computational microscope, which gives them access to temporal time scales and spatial length scales that are beyond what current experimental imaging can access, and to give the dynamics, the actual movements, that how these structures interact, and show people how those biological molecules work. So one of the things we're interested in doing is taking uh, data from different experimental imaging sources and using that data together in so-called hybrid molecular dynamics simulations to produce an atomic structure that is better than any of the individual components. And one of the key areas where this takes place is taking low resolution structure information from electron microscopy and combining it with high resolution atomic structures from X-ray crystallography. The electron microscopy data are sort of volumetric data. It's called an electron density map, and it's very low resolution compared to X-ray crystallography. And so we can't see the individual atoms, but the density values, the volumetric data we were working with, does map onto those atomic structures. And one of the key things we want to be able to do in working with that kind of data, even early on in the preparation of these kinds of simulations, is to be able to label different components of the structure according to their connected regions of density. And so these correspond directly to parts of the atomic structure that are a particular subunit. And so we want to be able to index and label those things, and then we can, once they've been labeled, using what we call image segmentation algorithms, we can refer to those, and then they can be specifically colored or selected, and we can begin to operate on that atomic structure information in much the same way we would with a computer-aided design tool working on gears or other components. And so we need to be able to perform this work, and that algorithm is the key step in doing this. So VMD does a so-called scale space image segmentation, where it iterates over many steps to produce a number of different candidate segmentations. A segment is basically a grouping of voxels that have similar density values, and with a certain gradient criteria. And this calculation, running on conventional CPU hardware and conventional serial algorithms, can take several minutes, and the bigger the density maps are, the longer it takes. State of the art image capture techniques in the structure determination area, the microscopy, is now pushing into the gigavoxel regime, and next generation imaging techniques will probably produce much larger data sets. So our goal for small data sets is to make this algorithm so fast that it's interactive. So where a complete segmentation process would take much less than a second, And for our next generation problem sizes, we want it to remain, usably interactive. Maybe it takes a couple of seconds to calculate a big density map that has 6 or 7 billion voxels, for example. So one of the properties of this algorithm, there are a whole bunch of different kernels, but we went and looked for a kernel that was sort of outstanding as something that consumed an inordinate amount of time, and we'll talk about this as we get into the trace. And these kernels, there are many different kernels, but we execute them in many passes. And their function is to basically merge groups of these voxels together into what we call a group, and the different groups then, over successive iterations, the groups continue to be merged and merged and merged until we get down to a number of segments that is logical for the atomic structure that we're looking at. So really what we're looking for would be a segmentation that gives us one segment per monomer. So if we have a multimeric complex or something, or something like a virus capsid that has a bunch of repeated structure, our goal would be to give one segment per subunit, and that's really what we're after. And so anyway, the segmentation won't give us exactly that, but we'll get a series of these, and the user will then pick the segmentation that is most desirable from the results that the algorithm produces. But the key thing we're going to talk about here is, because the number of segments at the beginning, we have one segment per one group, one group per voxel. We start out at that extreme, and as the algorithm runs, we get down to numbers like 100 or 50, or at the end of, in this example, 4. And so we do a lot of algorithms that involve reduction operations of various kinds. And so when those reductions take place, if we end up doing things like atomic operations to a shared value for per group, for example, the number of collisions increases as the algorithm progresses, because we have a smaller number of these groups, and therefore this becomes a performance inhibitor. And so we'll talk about how we determine that in the tool, and how we address the performance problems that creates. So just as an example, we have a find max values kernel. This is one of the kernels, one of several that we have to run as the algorithm iterates. And its goal is to, for all of the voxels that are members of a particular group, its goal is to basically go find the maximum value that exists for any of those voxels. And because any voxel could be a member of any group, we don't really have a nice memory access pattern. It's going to be a randomized memory access pattern. So any given voxel could be a member of any group. At the beginning, every voxel is a member of its own group, and as they've been merged and merged and merged, we're going to have a greater tendency for neighboring voxels to end up being members of the same group. And so that's interesting, because that provides us with a performance optimization opportunity. And so you can see in this original code, which is very simple, we're basically looking up the group number for a given voxel. We then fetch the value of that voxel, and we convert that to this intermediate integer representation, which we can use to compare against all the others. And then we perform an atomic max on that integer representation of that voxel value, and we put that into the storage location for that segmentation group. And so you can see, if I have several neighboring voxels that are members of the same group, they're all going to try and update that same target memory location in global memory, and that's going to create a performance issue. And so we want to come up with a better way of doing that, but uh, this is the kind of thing you can find very easily using the Insight Compute tool. And so we'll go into analyzing the original code, and then show you how we can make it better.
Yeah, I show here the Insight Compute, and I already opened the report that John's team created. I have the original report open here, and what you currently see is the details page, which is our report page that summarizes all the information we collected from the kernel. And you can see at the very beginning, as John already indicated too, is like we go through that report usually from top to bottom. It's organized in a top-down approach, and it's organized in these sections. And the first section here is like the GPU speed of light sections, which is a section that focused on the overall performance that this kernel achieves on the GPU. Speed of light, you can think of like this is the percentage of peak performance that you achieve, and the chart here shows that this kernel, in the way it was run at the very beginning, doesn't utilize the compute resources much, and also not memory. So both are like under 15%, which already shows like that something is not working as expected, and we have probably some ways to make this faster. Um, in addition to the numbers and the sections, you also see like the rule system I mentioned earlier is already showing that it detected automatically something, in this case like exactly what I said, that both are pretty low and that we should look at other sections. So I just follow this and click on this link and get to another section, which is the scheduler statistics section. This one cares for how, like, the warp schedulers, how busy they are and how efficient they actually issue instructions over time. What we can see here is like that our theoretical warps per scheduler are like at the theoretical max. So we run at 100% occupancy, theoretical occupancy. At runtime, we do have active warps, like they are a little less, but not worrisome yet. Every warp scheduler can issue one instruction per cycle. We have more than like around 5 active warps per scheduler, but then the difference between active and eligible are the stalled warps, and this one already indicates pretty much that all the warps are stalled and not ready for issuing the next instruction, which then kind of causes us that we barely issue any instruction and don't make any forward progress. And again, the rule would explain that also in words. It kind of points out we only issue an instruction every like 65 cycles, which is fairly slow. And if you want to understand a little more what kind of stalls are there that cause us all the trouble, the warp state statistics shows you all the stall reasons over time, and it shows that the top reasons, they are ordered here by reasons, and the top reasons are drain, long scoreboard, and LG throttle. If you don't know, again, like what these all mean, the compute profiling guide will explain those, but also in the tool for the top reasons we have the explanation for those here at the bottom as the rule system as well. In this case, all three of them, like drain, long scoreboard, and LG throttle, are all memory related. Drain is pretty much at the very end of the kernel if you have a lot of outstanding writes or reductions in this case. Then before the kernel actually finishes and exits, all these kind of operations have to be completed, and that drain out pretty much at the end is something that causes a lot of stalls here. Long scoreboards are dependency between instructions, where you make a global load, for example, and then you have another instruction that has a dependency on the result of that. That is a long scoreboard and needs to be resolved until that warp can make any forward progress. And LG throttle means you overload like the pipeline that is issuing all these memory instructions, and there are too many coming in at the same time, and then it's like we cannot oversubscribe that pipeline, and therefore you get throttled, and you can only make forward progress once that pipeline becomes available again. To understand where in our code or what that causes, we can go down to the source counters. That's the tables I mentioned at the very beginning, which are new, and you see the same reasons over here from the sampling data. So you see again, like the first line is the drain, and we can just click on here and it gets us over to the source code where the source is. This is pretty much the code that John had on the slide, and on the right side you see the SAS code. They are correlated, so if you see, it's like click on the left side now, and you see that on the right side the code gets highlighted that is correlated or generated by the compiler for that line of code that you selected on the left. And again, If you now look at the code here, either on the left or the right side, we have the metrics, the sample data, and you can see like how often each line or each instruction on the right side is executed. And if we look at that code a little more, because it's kind of fairly small, even in this SAS code, we can see like at the exit down here, the instruction after the exit hangs pretty much because of all these drain instructions. This is like we would like to exit, but there's still outstanding work to be done. The next highest reason would be here. These are the LD throttles, where we do the reduction, and if you hover over and you don't really know what all these operations are, if you hover over, the tooltip will tell you what all these instructions are. This is the reduction operation. We execute so many in this case that we just have to wait that the pipeline can access more. And that is also one of the issues that you can see here. Our grid size up here is like 16 million in size. And we actually issue like 16 million, exactly the same amount of 16 million individual reductions. And that is just like oversubscribing that pipeline, and also causes that we have to wait at the end so much, because a reduction is an atomic operation, and you need to then, if they access the same output value or the same pointer that you want to change, then you have the issue that you have to serialize all them, and that takes time. If we now compare this, I go back to the details page, and if we switch to the new report, this is after the code change, where we now try to use the shuffle operation to do an intra-warp comparison first, and then if a neighboring thread has the same group, then we can first do the maximum local, and then only do the atomic operation for the maximum within the warp for each group. And this is the report. And before we dive in, I want to also show that the baseline that I mentioned at the beginning allows you to compare two reports. So I have the old one open. I click on Add Baseline on the top of that report, and then I switch to the other report. And now you can see that I have in that blue color my current new report, and in orange the baseline, which is the report before the code change was made. And now the report, all charts, all the metrics now will show both values, or the current value and the percentage change to the baseline. You can add multiple baselines if you want, but like in this example, we just want to compare those two operations. We start the same way than we did in the first time. You already see like that the speed of light, the percentage of utilization went up in both compute and memory quite significantly. So this is a very good improvement of like making more use of more of the usage. You can also already peek ahead in the header up here, where you see the total time this took to run, and you see like we improved that roughly by a factor of 3 by making that change. We also use a little bit more of registers, but we see later that this doesn't impact occupancy, so we are still running at 100%. And that 3x improvement kind of also shows that we now use the GPU more efficiently. If we compare the same charts that we had before, this is what I mentioned. We still run at 100% theoretical occupancy. We do have more active warps available now too, but most importantly, we now have a lot more eligible warps. So if you see, before we had like 0.04 eligible warps, and now we are at like 1.12 per cycle, which is great, because now we issue roughly every other cycle. So if you look at this is like 0.53. So now we issue every second cycle, compared to previously every 64th cycle or 65th cycle. So that makes that huge difference in performance. You could say like, yeah, we if you look at the instruction mix, we do issue a lot more instructions. So if you look here, since we have to do now the comparison between, there is more math instructions, but it doesn't hurt us, because ultimately that kernel's performance is like directly related to how many reduction operations we do. And if we go to the source code again, you see now, instead of that one line that we had before with just like calling the atomic max, we have to get through all of this math code and the warp shuffle here, and that comes with own kind of stall reasons itself. But the important part is, if we look at the reduction operation over here, which is this is the return, sorry. The reduction operation, it was up here. Um, then you see that this one's no longer like having those stall reasons that it would have an LG throttle. It also is, while it's executed from a warp perspective the same amount of time, we now only execute that for 2 million threads and not for 16 million threads. The grid size is still unchanged, nothing else has changed, but that reduction made a big change, so that it's like that pipeline is not oversubscribed anymore, and now also the atomic operations are so much less that this can be done in a lot faster time. And in the remaining time that we save, we can execute all these math instructions up here. One interesting thing to point out is also this loop in here. The compiler kind of optimized that and unrolled it for us, and you can see that with the correlation. So there is a pattern of like it unrolled 4 times, which makes it even faster for us, and there's more opportunity now for the compiler to kind of optimize this and make more efficient use of the available units, and we don't oversubscribe just one and have one oversubscribed and pretty much all others not used. Now it's way more balanced. To go back to the slides and kind of finalize this, John mentioned they are already like different. It's an iterative approach, and there are different iterations that you go through with different sizes of what they are, and there were already different implementations as soon as the number of groups fit into shared memory. But I wanted to show, like in this case where it was very slow before, which is like pretty much before we can switch to shared memory, where there is a high likelihood already that your neighboring or the threads in your warp are already in the same group. We can speed that up quite a bit. But I also want to point out that for the first iteration, where John mentioned like every voxel is in its own group, we actually made it a little slower. So there is like a balance between kind of the first iteration and this other one. But what's interesting is like you can see that the optimized kernel has somewhat a consistent performance across those first n iterations, while the other one, because of the atomic collisions, kind of increases, and therefore performance went down over time, while in the other case we can counterbalance that and have a good speed up. So that is one example how the tool helped kind of to identify this and made this special case a lot faster. John, I hand it over back to you so that you can introduce the NAMD use case.
Yeah, thanks. So yeah, I guess the only thing I'd say is, so this is a great example where you can, with the tool, you can collect the profiling results. That's one thing. Maybe Magnus, before we go on, I wanted to show that to them. Can we show that we collected not just the one kernel run, but actually a large number of them all at once? Can you show them the summary page?
Yes, I go back. I can let me quickly clear the baseline and then go to the summary. This is the yeah.
So this is, as I described in the beginning, we don't just run the code one time. You can see there are a large number of kernel launches. And one of the things that I really like about Insight Compute is it will automatically capture and profile all of the different kernel launches in your algorithm. And you can see what the name of the kernel was, what hardware it ran on, how many cycles, and the speed of light summaries that are the same numbers you saw on that details page. And you can see, if you go and look at a particular algorithm like the find max values kernel right here, you can see there's one of the first runs. And then we can go look down at the one we were looking at later, and it has different run times and so on. So this is a data dependent kernel. If I run the kernel 5 different times with 5 different inputs, I'll get 5 different run times. Although the new algorithm, because it does this intra-warp reduction, it is much more performance stable than the other one, the original implementation was. This is a good thing to have in the tool, because if you have a data-dependent algorithm like this, your different collections will show its behavior over a series of iterations. And so this is one of the features of the Insight Compute that we found really particularly helpful for us, because both in VMD, where we have this iterative algorithm here, But also in NAMD, we have a feature called multiple time stepping where different kinds of force calculations are done on different steps. And that means that the same algorithm behaves a different way, or we have a templated kernel, and we're going to use one of the other template instantiations on a different time step. And so it's great to have this feature in the tool. So then we can go back to the slides. And so, yeah, so NAMD is the tool we developed that does the actual parallel molecular dynamics simulation. So, this is what actually calculates forces and accelerations and velocities for all these atoms, enforces the laws of physics, and allows us to study the dynamics of these biomolecular structures. And let me click here and get control. So NAMD decomposes its dynamics calculation into a large number of independent force calculations. So there are so-called angle forces, pairwise non-bonded forces between all the different atoms. So these are electrostatic forces. And then there are long-range particle mesh Ewald forces that are done less frequently and at a larger distance. They're for atoms that are far away from each other. And NAMD decomposes its calculations both in terms of multiple different time steps. PME is done 1/4 as often as some of the other calculations are. And some of these are more important to our overall performance profile than others. So if I were to summarize in general, generally speaking, for most molecular dynamics codes, but NAMD in particular, you would expect that the non-bonded forces are the dominant place where you spend most of your runtime. And that's just because this is the direct summation of electrostatic related forces from atoms that are nearby to each other in space. And so that's where the lion's share of the work is. There are, many other kinds of kernels that we have to run, but this is where most of our performance comes from. So if we can make this particular kernel faster, we will end up making the entire program faster. Even though we may have accelerated all of these things on the GPU, this one is the one that gives us the greatest bang for our buck in terms of our optimization efforts. So it turns out we've, working on this code for a long time. This is one of the parts of the code that's been accelerated the longest. And when we first adapted NAMD for Kepler hardware, it began to be possible to use warp shuffles to do efficient reductions. And we came up with collectively a scheme that used a warp shuffle to do some of this non-bonded calculation. It turns out, though, that one of the deficiencies in our original implementation was that the warp shuffle, because it has to involve all the threads in a warp, this meant that we had to perform the warp shuffle outside of some branch tests, and so it had to be done every time, even for atoms that were ultimately marked to be excluded from the calculation, and that harmed our performance slightly versus what we had come up with later. Working with one of our dev techs at NVIDIA, he identified an optimization opportunity that would let us do the same thing in shared memory instead. And because it's done less often, it's done inside of one of the other branch tests. So it's you can see right here, we're going to do this less often than the other case. This allows us to use shared memory, and this work is only done when it has to be done. So that means we've saved a little bit. We've shaved a little bit of extra work off because we're not using a warp-wide reduction operation. And then that combined with some other optimizations to use a structure of arrays, memory layout for some reductions in force arrays, those two changes and some compiler flag changes ultimately give us a roughly 20% performance increase for this particular kernel. And so now we'll show you how we can, measure that performance and what impacts that had in the tool itself. So let's go ahead and take a look, Magnus.
Yeah, I prepared the same thing here. So we go through the report again. I have both loaded for this example too. We look at that non-bonded force kernel. And the same here, we start out with the one before the operation, and I want to show how it was possible to identify those changes to get that performance benefit that John was explaining. A big difference that you can already see from just looking at the speed of light section is like we started out with a highly optimized kernel. So these kernels were looked at by many people already and kind of squeezed out already a lot of performance. So we start with something that is already kind of in that mid-range of like 50%. And so it's not immediately obvious kind of from just looking at this is like, oh, this something is holding us back. And we need to go in a little more detail in seeing like what it is. In this case, I want to point out like the memory breakdown in this case. So the chart itself only gives you the overhead of like SM versus memory, and it's a good first indication. The breakdown kind of gives you the like a stacked bar for this down here. It's not really stacked; it just shows you all the sub reasons for this SOL bar up here, and the highest one drives this value. But you can also see all the other reasons that that might not be the top reason to drive the bar up here, but like to give you also all the other reasons. And a few things that we can see from the breakdown is we issue quite often because issue active is like at 50%. On the memory side, we see that the waveforms going through the load store unit is quite busy and is the highest. And if we scroll down a little more, I also want to point out that here you see like the roof line, and you can see just for people that didn't see that most often is like that roof over here is kind of driven by your memory throughput. The other two lines is 64 FP64 and FP32 kind of roof lines, and the achieved kind of point in here that you see in purple, this is how close you are to that ceiling. And you can also see here already we might have space to grow a little to the right and up. But not like directly, like there's only like a little bit improvement that we can go if we would go straight up. So if we want to achieve more performance, we have to move kind of to the top right. One other thing that I want to show out, we already identified that memory is maybe something in the breakdown of the SOL. This is the memory chart, and what you see here from left to right is like your kernel on the left makes requests to all these different memory spaces: global, local, texture, surface, and shared. You see how many instructions are executed, and then it goes into the memory hierarchy in blue, where you have the L1 text cache first. That then talks to L2, and then you can either read from system memory or from device memory. So you see on one kind of overview here quickly how much data flows through that system and what parts of your memory system are most utilized. So in this case, we can look at and say like there are some global memory reads. There are a lot of local memory reads, like 12 million instructions issued, and quite some data being requested. John already mentioned that the operation kind of that helped here was shifting more to shared memory. The original kernel doesn't use any shared memory, but an indication that something like that might be possible is that there is a lot of local traffic, and your cache hit rate in L1 is fairly high, which indicates like it's likely that we access the same data multiple times. It's not just the L1 cache hit rate that's so high, it's also like even though there is substantial traffic between L1 and L2, even the L2 cache hit rate is pretty high, which kind of further indicates like, hey, maybe there's something we can shift into shared and repeat just keeping it in shared and accessing it there, and shifting it out of kind of this more expensive L1, L2 hierarchy, so that we know for sure that we don't ever have to go for L2 for that data. There is more details in the tables below. You can see the same thing here in more detail. But I would like to also point out here that I would like to show the instruction mix. This is the number of instructions that are executed for this, and you see like that the LDS, which is like the shared memory, is kind of in the top three here, and the shuffle is already the shuffle is down here. If we now compare this to the new report, and I will do the same thing and add this as a baseline before, and we look at the baseline now again. In this case, if you optimize a kernel, you see over here the original kernel was close to 3 microseconds, and the optimized kernel is roughly 20% faster. You see that because it's faster, it doesn't necessarily mean that you always reach like a higher speed of light. In this case, it actually went down, which doesn't mean it's less efficient. We are faster. It's just we use different units and balance it out a little more even. And you can see that in the breakdown too. A lot of them went up. But the top reason went a little down, which just means like what used to be our bottleneck earlier is now a little less. Therefore, we made use of other units. And the same in the roofline chart. You see the ceiling is the same because we run it on the same GPU, but the old data point is a little to the left of the other one. So we increased arithmetic intensity a little bit, and we improved our performance in flops per second a little bit too, because that dot is a little higher than the one on the left. So it's a nice way to understand like what happened to that kernel over between those two iterations. I want to open the memory workload analysis again and look at the chart. Just to see here that you can already see a lot here what happened in the code. We had like 12 million instructions for local memory. We reduced that a lot to only 3 million. Correspondingly, also the traffic went down quite a lot. We still load from global the same amount of data. The kernel has to access the same amount of data. But now we added a lot more instructions down here to shared and a lot of traffic to shared. But all of this is guaranteed to be served by shared memory and doesn't have to go back sometimes to L2. Hit rates are still good on those two. Nothing changed here. Overall, access to device memory went down a bit because we keep more data now closer to the kernel, and that's where the performance comes from. I also want to quickly go down to the instruction statistics and just show you again what has changed. The biggest changes are the shuffle instruction is now used a lot less, and that's what John pointed out, where we're saying like previously you had to execute this because all participating warps need to participate. Now this is reduced, and we need a lot less shuffle instructions because we moved into shared memory. Obviously, we do a lot of shared instructions now. That is in addition. But already by looking at this, you can also see there's a little less branching. And in total, if you look at the warp statistics, we are roughly at the same kind of cycles between instructions issued. So this hasn't changed much, like a 2% change. If you look at how often we execute, we are still in both cases roughly issue an instruction every other cycle. So this value is at 0.5. But what is interesting is like that new kernel issues like 12% less instructions, which if you issue at the same rate and you can issue a lot less instructions, by no surprise, the kernel will be faster. So like 12% of that improvement roughly comes from the idea that we issue the same at the same speed, but we found a way to do the same work with less instructions that can still execute in the same kind of performance. So that helps a lot of kind of getting an additional performance improvement out of this. And the idea of showing this way is like to see is like if you make a change and you just do that diff before and after, it helps a lot to understand like did you achieve what you wanted, and also like what other effects might that have on the whole kernel, because you might optimize only one value in the whole report, but if you don't look at all the others, then you might just create a different bottleneck that's even worse than the one you tried to work on. So the idea of being able to diff all this data and having a report that is that detailed is like allowing you to kind of have that holistic view of like what did your kernel on the GPU, and where are areas that I can improve further. John, any comments before I switch back to the slides?
No, I think that's a good summary. Yeah, the basic idea here is just making optimizations that make the kernel just slightly more work efficient. Allowed us to shave off those warp shuffle instructions, which had to be done, regardless of the true false exclusion parameter. and now they're only done, now that it's in shared memory, we only do them when they have to be done. And so it's like you said, we just deleted some of that work, which was not serving a purpose, in favor of a different way of doing the same calculation.
Yeah. Then I switch back to the slides to summarize what we tried to show today is like kernel optimization is always kind of a combination and goes hand in hand with like a good tool support, some documentation that you can understand what the GPU is supposed to do and how it works, and then there is that level of experience. So if even if you are new to the tool, just run it with your examples, make some code changes, run it again, and diff the reports so that you can understand of like, hey, what I did in the code reflects this way in the metrics. That's one way of kind of getting to learn the tools, and we provide increasingly good documentation. We try to make it better with every version so that you have enough material to kind of understand what the tool is showing you and what all these metrics mean. There are common patterns that you will see over time. Often we see like uncoalesced memory accesses, which are now covered by rules, so you can directly jump to that one source line that has those. Today we focused mostly on like efficient reductions, and we showed like one case where it was useful to switch to shuffle instructions, and then another case where we were already at shuffle instructions, but there it was actually more useful to switch to do it in shared memory. So there are different patterns that repeat, but I hope we could show that the tool kind of guides you towards those, and you can make use of the metrics in the tool to get to those and understand what's going on. Also, something to point out is like the kernels we optimize today, they were optimized before, either a long time before for a different architecture, and that's a good reason to look at them again because things change over time. There are new features coming for new architectures. Sometimes there's also just a balance shift in memory versus compute, or there's a pipeline that is now faster. And to kind of really get out the last like 5%, it's worth to even revisiting those from time to time and see like if there is something new or something has changed to make sure you are looking to get the best performance out of what you have. And then for Nsight Compute specifically, I hope I could show you that all these changes could be identified in those reports and motivated by like if you go through and understand like your limiters and go from a high level to a low level through that report and follow the rules and kind of go step by step, then hopefully it guides you in that direction where you can make the next change and find the next performance benefit for your kernel. The rules help, so run the rules every time if you can, and we will add that in addition. And that way you get even more guidance and more part of the documentation that is interesting for your specific kernel in the tool. Then you don't have to read like the whole document, but only the part that actually helps. And over time, you get a good understanding of what happens in the tool. John, any feedback from you from using the tool that you want to share?
Yeah, I would say, I would emphasize the things you already mentioned. In our development plans going forward for both VMD and AMD, as we go and adapt the codes to run on Ampere, we know already from looking at these profiles on the existing hardware where we're likely to face shortfall in performance because of over reliance on memory bandwidth instead of flops, or maybe ratios of different functional units will change on Ampere versus Volta. So we have some areas where we expect to find little things that we're going to address. And then there are other cases where, in the long term, we have sort of alternative algorithm formulations like the non-bonded kernel on NAMD. Right now we use interpolation table for some of the force calculations. This is a decision that was made back, in 2007, and it was mirroring what we do on CPUs. And in that time frame, with the performance characteristics of that hardware, these were the right decisions to make. But going forward, if we start, we feel we're getting close to crossing a threshold where we would be better served by doing pure floating point instead of using those interpolation tables, because the changing performance characteristics of state-of-the-art GPUs. And so that's a more radical change to the structure of the algorithm than even some of these little optimizations we were just talking about today. And this is exactly the kind of thing where we would want to do that work or do that prototyping within Insight Compute, so we can sort of see, is it heading in the right direction, or can we already see if we, how many, if we have several such tables, can we move one to being all floating point? Is that enough? Or should we move all of them to being pure floating point? Where's the balance point likely to be, both for existing and future hardware? And so those are all exciting things. Some of the things, that I think were particularly nice about Insight Compute that I already mentioned are its ability to capture a large number of kernel launches all in one session. And so that, for both NAMD and VMD, where we have these data dependent algorithms, or in NAMD's case, we have multiple time stepping where certain kernels or certain math are only done once every so many steps. And we have heavily templated kernels. It makes it a lot easier for us to evaluate the behavior of the different template variants or the different data types that go in on different time steps or different phases of an algorithm. That's something that we really like. And some of the things I'd like to see in the tool going forward are just incorporating more features to allow us as a team to efficiently share those reports with each other. Right now, if I work as an individual, I can collect the performance data and I can send one of my colleagues the report, but I have to make sure I give them the matching source code, things like that. So we're hoping that as the tool evolves going forward, there will be more features to sort of build in source code snapshots that go with the report and to capture those things more automatically. And uh, other things are just to make it easy to generate things like talking points or slides for internal discussion. So, for example, on the summary page, we can collect all those performance data for a huge number of kernel launches. It'd be great to be able to mine that interactively. I mean, you can already do some of these things by filtering with NVTX. We want to be able to do the same things with just the kernel names or the different template instantiations. And it'd be great to be able to export filtered selection straight into a PowerPoint slide and show all the performance data as a series of bar charts, things like that. Those are, just little common things that we as developers like to be able to do when we're communicating amongst ourselves or the other stakeholders who are contributing to the development of the software. Big programs like NAMD and VMD, NAMD in particular, we have a lot of external contributions from outside developers, and so we're going to have to teach a lot of those outside developers how to make their code performant in the state of the art NAMD that now runs at very high performance on the GPU. And so we'll be showing them how to use these tools. And so everything that sort of streamlines that will be a great development.
Yeah, awesome. Thank you, John. And yeah, for everyone listening, I think I use that as saying on one side that we already have a full roadmap from the feedback that John gave us, but I switched to here to say, like, if you have any feedback for us too, feel free to let us know. Then we work on the problems that are actually out in the field and make it better for all of you. I listed the links here. Links to the documentation. If you have any questions for the tool, the forum is a good way of looking at what other people already ask, or ask your own question. We try to answer pretty quick in the forum. If that doesn't work for you, we have an email address where you can contact us, or use the feedback in the tool. If you go to help and send feedback, you can make feature suggestions there, or send us bug reports to make the tool even more stable. It allows you to configure what you want to send us. You don't have to specify an email there either, or send us a screenshot. We only collect the data you enter there, and you will see what is sent to us. So that are all good ways to kind of provide similar feedback to what John just gave all of us, to the team that works on the tool, and then we can improve and make it even better. That is all we prepared for today. Thanks for your attention. I hope we see you all soon.